Marlene Üblacker. I'm from the IGT Berlin in Germany, and yeah, I work together with Jaime and Aphrodite. And I think Jaime already gave a very nice introduction to our working group. So I currently work on the identification of freshwater habitat patterns. I do this by clustering subcatchments with similar environmental conditions. And my focus is that I want to identify especially the small and rare and unique habitats, which then should finally go as an information to spatial conservation level. So in the moment, I'm using the Kinesis algorithm. It's a very fast and very common algorithm. When I started, I wanted to test a lot of different clustering methods, but then I figured out that for most of these methods, you need distance or similarity metrics, which can get easily very large, especially this data set, and then you need a few hundred gigabytes of RAM, which is not making. So I use the k-means so for the k-means, you don't need the distance metrics, you just fill your data and go into it. So this week here, I tried the spectral clustering, and I did this by just using a subsampling of my data so that I can create these distance metrics and then try to shift my others, the belonging of the clustering of the others. Yeah. So here you can see, as an example, I took the Po River Basin. It's in the north of Italy, and here you can see the very dense river stream network Giuseppe produced, and it has more than 380 stream reaches, and of course also the depending subcatchments.
So that's one of the types.
No, it's just a river basin. It's it's really, and it's not a really large basin.
Okay.
So yeah. So in comparison, the Danube River basin, I think, has over 4 million stream reaches. So I also plotted the elevation so that you can see. So you have here these mountain regions, which elevations up to more than 4,000 meters above the sea level, and then here it goes to the valley, and here to the sea. And here in this area, you have urban area and also agricultural area. So yeah, I'm using the data Jaime produced, and I don't have the code here included, but I normally use org to filter the subcatchments IDs I want to use from all the tables Jaime created. Yes, and I also did this time my work in Python. I'm really new to Python, and sometimes it took me quite some time to figure out to adjust the code so for my problem. So in total, I'm now using 74 variables for my clustering here. Just a few examples for the different categories I have. So I have some variables for some geomorphological variables like elevation, the stream slope, the stream power index, or the distance to the outlet. Then I use the gel cell biochem data. So the biochem, so the just 19 variables. So for example, one of these variables is the mean annual temperature or the mean annual precipitation. You also have information about the coldest months in the year and the warmest, and also climate, seasonality. And then I use the ELSA length cover data for 2018. I have 22 classes, and here just an example. So for cropland and forest, and they are in. So you have the proportion of each land class within the subcatchment. So then I took a sample of my data set of 2,000 sampling sites, which is roughly 5%. And as my variables, the range of my variables is very different, I scaled it or I normalized it by the standard deviation. So I did this for both data sets, so for the whole data set and the sub data set. And then Antonia advised me to explore my data a bit with the principal component analysis to see if the subcatchment, the subset is somehow representative for the whole data set. So the principal component analysis is just simply said, it's summarizing the information and gives you the principal component, which is describing the most of your variables. So I tested different numbers of principal components and then realized that my data is mostly described by 20 principal components, which describe a bit more than 80%. And as you can see here, so it's similar for the whole data set and the subset. And I also looked at they're a bit small, but it's it's showing you the explained variance ratio. So the principal component one describes almost 0.4, and and then it's yes, and then there was otherwise also. So I plotted the first and the second principal component to look at my data, and here the color is representing different variables. So above you have my whole data set, and below here you have the subset. And for that's also elevation. So here you have in color the elevation and then distance to the outlet and the minimum temperature, and you can see that you can already see some clusters. But the structure doesn't change too much when you're looking at the substance. There's still some clusters visible.
So what was the conclusion there?
That it should be possible to use the subset, and
So this computer can be generalized to other bases.
Well, for these
data
spaces,
So for every base, then you need to know this game.
I would need to check if the subset is representable.
yeah, you have to use some sort of metric that can show like to which extent you can use a subset to train a model, like either a clustering technique or like a neural network. How you can use that as like a representative number of samples that kind of covers all the variance that's having the whole data set. training like all bunch of data, then you can just run predictions for everything else, right? So that's what we're trying to do. Because as I was saying before, all the fancier techniques usually they demand like this distance matrix, which basically is like number of samples by number of samples, so it's like a massive matrix. You cannot store memory, right? Like then it's a technique to verify that. Like you can use different strategies to.
But this is we are comparing only graphical.
Yeah.
Oh yeah, she has the quantification on both, right? So, like the numerical quantification was on the top, like the previous cell. Yeah. And also the absolute values, like in the cell of both.
Okay. So we can say that around here you have explained it.
Yeah. So this is visual, so you can see that like indeed apparently both the subset and the whole data set they are perfectly explained by the same number of components, and the total amount of the explaining variation is exactly the same. So like basically the subset very well like converts the whole variation that you have in the whole data set. So you can use that.
Yeah, so for the spectral clustering, you have to define your number of clusters you want to have. So to do this evaluation, I use the silhouette score and the Kalinski-Haber score. The scores evaluating how similar an objective is to the cluster. And compare it compared to the other clusters, and how good the clusters are split. So yeah, I ran these two graphs multiple times, and it's a bit changing when you run it multiple times. And the first time, both say 3 clusters is the best, and here you can see the silhouette says 4, and the Kalinski-Haber says 3. It's always often the thing that the starting point maybe got chosen a bit different, and then it can vary. Yeah, so that's probably a problem that my clusters are often overlapping and are not that well separated. Yeah, and then I come to the spectral clustering. So the spectral clustering could have a better performance in the clusters I'm searching for. So the k-means, it's better in identifying clusters which you have one cluster, and then the next cluster is surrounded by the next cluster. So spectral clustering is a bit better in identifying this kind of patterns. Further, the spectral clustering is based on graph theory, and I hope I can explain it a bit. So you first similarity or the distance matrix gets created, which describes the similarity to each point. And then the clustering reduces the objects which are not so similar, so that until you reach the classes you defined.
So again, the difference between the two is that k-means tries to find like centroids, like centers that might be representative of like clusters, and then you try to associate all the other points to this like
and it makes a partitioning.
Right, yeah. And like on the other hand, spectral clustering tries to find this distance matrix that basically it's a proxy for like how similar points are to each other. So instead of like trying to find a centroid which has to be representative for the whole cluster, which noise complicated, right? On the other hand, like spectral clustering just tries to lump things that sort of look similar to each other. Then you try to maximize the number of cuts that you can really grab to separate things that like have a higher degree of coherence. They are more similar, so you don't have like a representative for that cluster. You say you don't have a centroid for that cluster. So that's why it's better in theory, because you don't depend on like finding an archetype for a cluster. That's the view of spectral.
Yeah. Yeah, so I did the spectral clustering, and then, so yeah, I did the spectral clustering for the subsegment. So now I had to predict where my other objectives in the data set, to which cluster they belong. And for this, I used neighborhood metric. And yeah, here it is looking, so, okay, takes one object and looks for the 3 nearest neighbors, and to which these 3 nearest neighbors, to which cluster they belong. And if there of the 3 neighbors 2 belong to cluster 1, then this point will also go to cluster 1.
In theory, maybe you could use more neighbors though. You
What?
could use more neighbors. 3 neighbors
Yeah.
might be a little bit risky, yeah. Like, yeah.
I wasn't sure how you can decide which number of neighbors would be good.
You can do the same analysis that you're doing for the number of clusters on the top.
Also
Yeah,
doing
yeah.
a range.
Yeah, you can also use the elbow method. It's like at some point, if you keep increasing the number of neighbors, you stop changing the label for the points that you're trying to predict. Because then, like, more neighbors, more support, therefore, like, you get more stable, right? But like, if you keep increasing the number of neighbors, you see that there are more comparisons that you need to do. Because if I say, like, I'm trying to find the label for this one point, and I'm going to look at my 3 neighbors, then I have to run 3 computations, right? 3 calculations that I need to do. To say that you want support using 100 neighbors, then you have to do that operation 100 times. So like, takes way longer, and you have to call that thing in memory. So like, yeah, there is a sweet spot, of course.
Yes, and then I just exported my subcatchments NT and the K, the subcatchments, the cluster, the subcatchments belongs to, which can then be used for reclassing the raster file, or here in my example, I used the geo package and added it as an attribute to set the colors. Yeah, so that's the solution for 3 clusters. I need to say I was a bit surprised that it's only 3 clusters, because from my experience with k-means, which I ran not on the total data set, I always suggested clusters were always somewhere by 15 to 20 clusters. So yeah, maybe I have to analyze the subset a little bit more, how representative it is really, or if it's missing some very rare and rare habitats or small, yeah.
It's interesting how these plots are a lot like the elevation plots, right?
Yeah, you have really this the elevation, the cluster, and then here I think in this area is a lot of urban area. Am I right?
But the thing was, this data normalized? It was, right? Normalized the data, right?
Yeah.
Because I don't remember seeing the normalization. I remember seeing the peaking for PCA.
It was at the beginning where I also did the subsampling, and then I immediately did the.
Okay, yeah. Just to make sure that like elevation is not taking like all the importance, you know, because of the magnitude of the variable.
Actually, this area, I don't know why it's very similar to this, the blue one. So it's a super flat area. I don't know why I can't include the classes. I would expect it because these are like region with the same variable characteristics.
Mm.
So yeah,
That's interesting analysis to get all the points that are now inside of that cluster and see how it differs from the blue cluster.
Mhm.
And then you get to see exactly why that became a cluster.
Yeah.
So,
Yeah.
probably there is some variable that really make the difference. Maybe.
I also plotted the 4-cluster solution, and there it clusters really the main channel of the river, or the subcatchments along the main.
so the river became a cluster on its own?
Yeah.
And here, no,
No,
with the same number of classes.
no, that's 3 clusters, and then the 4 clusters, which was suggested by the silhouette
Okay.
score.
That's cool. Can you see that there is another stream, like a little door, like kind of an arc?
Yeah, this one I think is a canal that has this strange shape channel. We need to check on. I think there was something like this.
Which is the basin, actually. Name of the basin.
Okay, the pole. Yeah, it's the old pole. Yeah. North of Italy.
But you can see how robust is the green cluster. So like the green cluster, definitely there is something that's
That's true.
there. You know?
Can you list again the variable that are using?
All very.
I mean, more or
I
less.
mean, I will use the bioclim data, so this 90s.
Bioclim, so it's climate.
Then the land cover, the ESA,
then
and
cover.
then some of the values from the hydrography 90 meters, so
Okay.
elevation, flow accumulation.
So no soil,
No.
no
Couldn't use the
agriculture is the land cover. Because
Mhm.
this one is all one area where they do rice production.
It's one
Okay.
area.
Yeah, they could,
Mhm.
it could be something from the land coming from the land cover that is influencing that area. Could be. Okay.
Is there any city?
Sorry.
Is there any city? Is there-
So Milano is here.
So, would it be just one?
Yeah, but it's more.
Yeah.
It's more. You know, Milano is more over here. I mean, it's more compared to the green. Okay. Cool. Conclusion.
So yeah, just using a sample really decreases the running time, and you don't have to parallelly size everything. What I do currently, and yeah, and it allows to use different metrics, and then you can select for much more different cluster methods. But yeah, I mean, the clusters here are really, really large. And so I'm wondering if when I use just a subset, I'm losing some of the smaller habitats. So yeah, I need to do that more analysis here. To lose the one, yeah.
I think
Yeah.
it depends a lot on what's the level of granularity that you want to know. Because, for example, if you have 100 clusters, you're going to have, let's say, 10 clusters that although they're considered clusters, they are very similar to each other. So, like, what's the degree of like difference of between clusters that you expect? So, for example, we know that between the purple and the blue, there is a huge change in elevation, right? So, like, that makes perfect sense to place them in different clusters. Now, let's say that's like for the purple, we would have like 30 clusters inside of the purple. We should have like more clusters, right? Like to which extent that's beneficial to you, right? So more clusters is not better. That's what I'm trying to say.
Okay.
Yeah.
Okay, very good. Very good. More questions? Any other question? So yeah, I really like the fact that the way how you come up with suggesting with Antonio the sample, yeah, using the sampling strategy to see if all the variability has been explained, because we are quite often we can have a very small number of points, like for example for video with few species, but in some other cases we have a very billion of points that of course we cannot analyze all of them. So this is quite a very nice example how you compare with the principal component analysis, the explained variance. In other words, these two plots, they need to be extremely similar. And of course you can, this one was with what, 10% to 20%? The subset?
5%.
5%. So maybe if it's becoming, if it's not the same, you can increase the number of subset percent.
Yeah,
Okay.
if you go like to 1%, then you're gonna see that the exponent variance is gonna be very different between them.
Perfect.
So like, of course, more samples that you can use, the best, because then the similarity is gonna be high.
I know first I'm working from the cluster in R.
Mhm.
Been doing that for a while, and now we're doing in Python, which I think is really nice, amazing. So the question is, what is the feeling in terms of, I don't know, speed or flexibility, or you want
yeah.
to move now?
I have the impression when it comes to machine learning, Python is, how to say, that it's better implemented. So in R, there is not really a function that you're doing the k-means clustering on a subset and then just predict it on the whole data set. Maybe there are some ways, but they're not so well implemented like Python.
And probably there is also a larger community in machine learning Python, so a forum that you can read and so on. Okay, very good. Any other question?